This presentation is part of a lecture series on the C++ programming language by Michael Adams at the University of Victoria in Victoria, Canada. For those of you who might be interested, a copy of the slides for this lecture series can be downloaded from the website whose URL is given at the bottom of this slide. This presentation constitutes a work in progress. It's definitely far from perfect, but hopefully it's of sufficient quality to serve as a useful resource for learning C++. For the benefit of those of you who may be relatively new to programming, including many of my students, I'd just like to make a few comments regarding the examples that appear on these slides. Often, in order to make an example short enough to fit on a slide, it's necessary to make a lot of compromises in terms of good programming style. So some of the deviations from good programming style that are demonstrated by these slides are such things as frequently formatting the source code in utterly bizarre ways in order to save space, not including any comments in the code, using short, meaningless identifier names, and so on. So these things are truly evil. Do not ever do them in real code, but understand that for the purposes of examples and fitting them onto slides, it's necessary to do some of these truly evil things. In this section, we're going to look at another synchronization mechanism used in concurrent programming known as promises and futures. In concurrent programming, often the situation arises where one thread performs some computation and then it needs to pass the result of that computation to another thread. And this is essentially what promises and futures allow us to do. Promises and futures provide a one-time communication channel for passing the result of some computation, either some value that's computed or an exception that results from some computation, from one thread to another. And the basic idea is probably best expressed in terms of the figure at the bottom of the slide. So what we have is a producer thread, a thread that's producing some result, another thread which is consuming that result, and what we have is a picture like this. There's three different entities involved here. We have what's called a promise object, a future object, and then something called shared state. The promise object is the thing that the producer thread writes the result into. So the producer thread computes some result, writes the result into the promise, but underneath what actually happens when the producer thread writes the result into the promise is it actually gets written into the shared state, which is referenced by the promise. And then the consumer thread, which later, at some point later, tries to get the result that's been written into the shared state. It will access the future object that it has and try to read this result from the future object. And what this will do is when the consumer thread tries to read from the result from the future object underneath, hidden inside its implementation, will access the shared state, read the value out of the shared state, and give it back to the caller. You might be wondering, why is there this shared state? Why not just have a promise object and a future object and don't have this middleman, this so-called shared state? The reason for this shared state is to avoid lifetime problems, because if we do away with the shared state, then this means that we either have to write the result that's computed directly in the promise object, or the other choice we have is we could directly store the result that's computed in the future object. But either one of these choices will lead to problems, because there's the lifetime of the promise object and the lifetime of the future object are different. So if we try to store the result that was computed by the producer in the promise object, the possibility arises that the producer thread terminates, and this promise object is destroyed before the consumer has a chance to read that result. So it doesn't work to store the result in the promise object. And similarly, it doesn't work to store the result in the future object directly either, because what could happen is the producer starts to compute some result, then the consumer decides that they don't want that result anymore, so they destroy their future object. And then if the producer was trying to write the result into the future object, there would be no future object to write the result into because the consumer has destroyed it. So this is the reason for the shared state. The shared state is guaranteed to live as long as whichever of the promise or future lives longer. So as long as either the promise object exists or the future object exists, the shared state will continue to exist. So promises and futures are useful in both single-threaded and multi-threaded programs, although arguably they're much more useful in multi-threaded programs. In a single-threaded program, for example, you could use promises and futures to propagate exceptions from one part of a program to another. But really what's more of interest here is the multi-threaded case. So in a multi-threaded program, often you have a situation arise where you have two threads. One thread is performing some computation, and then later when that computation becomes complete, it makes the result of that computation available to a second thread. And basically this is the picture that was discussed on the previous slide with the producer thread and the consumer thread. But this raises some issues in terms of synchronization, because, for example, maybe the computation that the producer thread is trying to calculate, the result is trying to calculate, maybe it requires a lot of computation, so it's very slow to produce the result. So the situation could arise where the thread that's trying to consume the result tries to get the result before it's ready. So there has to be some mechanism whereby if the thread that's consuming the result tries to read the result before it's ready, it needs to be blocked until the result becomes available. Also, there's the potential that the thread that's consuming the result and the thread that's producing the result, they might both try to access the result at the same time. In other words, the producer might try to write the result at the same time the consumer is trying to read it out of the value that's been stored. So you have the potential for a data race, for example. So we need to have some kind of synchronization that's associated with promises and futures in order to ensure that bad things don't happen. We don't try to read the result before it's ready and so on. And this is essentially the sort of synchronization that's provided by promises and futures. In the standard library, the functionality of a promise is provided, rather unsurprisingly, by the class called promise. And as you can see from the declaration of the promise class on the slide, the promise class is a template class, and it's templated on a single type parameter, which is denoted by T on the slide. And the type T corresponds to the type of result that's written into a promise. So for example, if T was int, this means that the type of result that's being written into the promise is of type int. The type T can also, by the way, be void, in which case there is no data that actually gets written into the promise, but nevertheless the promise and its corresponding future can still be used for synchronization between threads. And also the case where T is void could also be useful for propagating exceptions, because not only can you store data into a promise, which can then later be read out of the corresponding future object, but you can also store exceptions as well. So even in the case when T is void, the promise and the corresponding future could still be used for propagating exceptions from one thread to another. So the case that T is equal to void can still be useful in practice. Objects of type promise are movable but not copyable. And there's two ways that you can write a result into a promise. One of them is by using the setValueMember function, which writes a particular result of type T, where T is the type parameter on this lecture slide. You can write a result of type T into the promise, which then can be read out of the corresponding future. The other way to write a result into the promise object is to use the setExceptionMember function. And instead of writing data, what this does is it writes an exception into, or stores an exception into the promise object. And then when the result is read out of the corresponding future object, the exception will be rethrown in the thread that's trying to retrieve the result from the corresponding future object. The result that's stored into a promise can be set only once, so the setValueMember function or setExceptionMember function can be only called once. And in order to retrieve the future that's associated with the promise, because in order to be able to have some other thread be able to access the result, it needs the future object that corresponds to the promise object. For this purpose, there's a member function called getFuture, which returns the future that's associated with the promise. So then this future could be handed off to another thread, which can then wait for the result to become available and then read it out of the corresponding future object. And the getFutureMember function can only be called once. So you can only retrieve the future object that's associated with the promise once. And then lastly, if a promise object is destroyed before storing any result into the shared state associated with that promise object, the result in the shared state will be set to a future error exception. And this will lead to an exception being thrown if an attempt is later made to retrieve the result from the corresponding future object. On this slide and the next, we have a summary of the members for the promise class. On the first of these two slides, which deals with construction, destruction, and assignment, there's not really too much to be said, except just a reminder that objects of type promise are movable but not copyable. So there's a move constructor and move assignment operator, but there's no copy constructor or copy assignment operator for this class. Next, we have the more interesting member functions of the promise class. So to begin with, we have the swap member function, which swaps the contents of two promise objects. Then we have the get future member function, which gets a future that's associated with the promise object. And we can, for example, get a future, and then we can give this to another thread, and then that thread can wait on the future in order to obtain the value that's written into the promise. Next, we have the set value member function, which is used to write a value into the promise, which can then be read out of the corresponding future at a later point. And there's a member function called set value at thread exit, which is very similar to set value. The only difference is the result that's written into the promise, which is read out of the corresponding future, is not made available until the thread that wrote the value into the promise exits. Then we have the member function set exception, which allows an exception to be stored into written into a promise, so that when a thread reads out of the corresponding future the value that's stored there, since there's no value stored there but rather an exception, that exception will be rethrown in the context of the thread that tried to retrieve a value out of the corresponding future object that's associated with the promise. And then lastly, we have the set exception at thread exit, which is similar to set value at thread exit in the sense that it basically delays the exception becoming available in the corresponding future until the thread that wrote the value into the promise exits. So again, when dealing with promises and futures, there's two sides to things. There's the promise side of thing, where the thread that generates the result writes the result into a promise. And then there's the future side of things, where the thread that wants to obtain the result reads it out of the future. And so far we've looked at the promise class in the standard library, which provides the promise functionality. Now we're going to look at the class in the standard library that provides the future functionality, which is called, rather unimaginatively, future. This is the name of the class. And the declaration for the class is as shown on the slide. It's a template class, templated on a single type parameter, which I've indicated by T here. So T corresponds to, or this template parameter corresponds to the type that's being made available through the future. So if T, for example, was int, this means that the value that or result that you're going to be reading out of the future object is of type int. By the way, T is allowed to be void, in which case there is no data that you actually read out of the future, but you can still use it for synchronization purposes. Objects of type future are movable but not copyable, as is the case with quite a number of types that relate to concurrency in the standard library. There's a member function called get, which is provided by the future class, and what this does is it retrieves the result that's been stored into the corresponding promise. And if the result is not yet available, in other words, the corresponding promise has not been written into, so there's actually no data that's available yet, then the get member function will block until the result becomes available. And then when the result does become available, then it will be returned. And the get member function can only be called once. Essentially, when you get the result, you lose the result that was previously stored in the future. So you can only get the value once. And lastly, there's a member function called wait, which simply waits for the result associated with the future to become available, but it doesn't actually retrieve it. So if, for example, a thread wants to block waiting until the result is actually available in the future, but not actually read it yet, it can use the wait member function. On this slide, we have a summary of the members of the future class. So with respect to construction, destruction, and assignment, really the only comment to be made here is just a reminder that objects of type future are movable but not copyable. Then moving on to the more interesting member functions, we have a member function share, which is used to transfer the shared state associated with the future object to a shared future object, and we'll talk about the shared future class a little bit later. The next member function we have is the get member function, which is used to retrieve whatever result was stored into the future. In other words, the value that was written into the corresponding promise object. And if the result's not yet available, the get function will block until the result becomes available. And if an exception is stored into the future, when the get operation will throw an exception when it's called. The valid member function checks if the future object refers to any shared state. The wait member function waits for a result to become available through the future. So in other words, it waits until the corresponding promise is written into with either an exception or a value to be read out. But the wait member function doesn't actually retrieve the value that was stored into the future. This you would have to call the get function in order to do this. And then we have wait for and wait until, which essentially perform a wait operation but with a timeout. So it will wait for a maximum period of time. If that timeout expires, the wait will return even though no value is actually yet made available in the future object. And the only difference between wait for and wait until is wait for specifies the timeout in terms of a time duration, whereas wait until specifies the timeout in terms of an endpoint in time. On this slide, we have an example of using the promise and future classes in the standard library. And the basic idea of what we want to do, we want to call this function compute value to compute some double result. And we want to call this function in one thread and then write the result into a promise. And then we want to read the result in another thread out of the corresponding future. So this is the basic plan here. So if we look at the main function, what we do to begin with is we create a promise object. And because the value that we want to store into the promise object is of type double, because we want to store the return value of this function compute value into the promise, and then read the result out of the corresponding future. So since the type is double, we want to use double here. So this object P is going to be a promise that is associated with a value or result which has type double. Then on the next line, for this particular promise object P, we call the get future member function, which gets the future that's associated with this promise, and then we save this future into the variable f. And just to save some typing here, I've used automatic type deduction. But the type here is essentially future, but with the instantiated with the type double. Then on the next line, here we're creating a new thread, the thread associated with the thread object producer, and it's going to execute the function produce. And we're passing in a single parameter P, which is the particular promise object that we just created. But because promise objects are not copyable, they're only movable, we have to use std move here. In other words, we have to use this move function, because if we didn't do this, then we would have a situation where we're passing by value. And passing by value, because P is not a temporary object, it's a named object, normally this would perform, the language would perform a copy operation, but because P is not copyable, we can't copy it, we would get a compile error. So instead we force a move to happen by using the move function here, which basically performs a typecast so that P is treated as if it was similar to a temporary object. It's safe to move from it. So this is going to create a thread which is executing this function here, produce. And if we look at what the produce function is doing, it's being passed a promise. And then what the function does is it calls compute value to compute the double value that we want to compute, which happens to be the value 42. And then it takes the returned value and it writes it into the promise P by calling the set value member function. Again, set value writes a result into the promise. So this is going to store the return value of compute value into our promise. So as soon as we create the thread, by creating this producer object here, this function in produce is going to start executing. And at the same time though, after this object, producer object has been created, this thread object has been created, the execution in the main function continues. So we'll go on to the next line. We try to get the value that's stored in the future by calling the get member function. And this, if the produce function hasn't proceeded to the point where it's actually set the value by calling set value here. In other words, if the main function executes really fast and we create the thread, and then very quickly before the thread has a chance to even execute, we get to this function call here, calling the get member function. This will block because the result has not been yet made available to the future object f. And then we would block here, waiting, and then eventually the thread that's running the produce function will eventually call set value on the promise P, which will write the result returned by compute value into P. And as soon as this happens, then back in the main function, this get function can return because the value has now been written into the promise. It can be read out of the corresponding future, so we'll read it out of the corresponding future, which is f, and return the value. So this is going to return some double, which in this case will be the value 42. We print it out, and then we finish by joining with the thread.
In the standard library, there's another class that relates to futures, which is called shared future. And I'm not going to say too much about the shared future class simply because it's very similar to the future class. Essentially, the main difference is that objects of type shared future are copyable, whereas objects of the future class that we talked about earlier are not copyable. And the reason that being able to copy these types of future objects is useful, the shared future objects, is it allows for the sort of usage where you create a promise and then you get many shared futures that correspond to that promise, and you hand out these many shared futures to many different threads, and then all of these threads can then wait for the result that's written into that future. In other words, shared futures can be used to have multiple threads read the result that's written into a corresponding promise object. And the reason this is possible is because the shared future objects are copyable. In the case of the future class, objects of that class are not copyable, so you couldn't use those objects in this way to be able to propagate the result that's written into a promise to multiple threads. And perhaps the only other thing that's worth commenting on here is another difference between the shared future class and the future class is that in the case of the shared future class, the getMember function can be called multiple times, whereas in the case of the future class, the getMember function can only be called once. On this slide, we have an example of using the shared future class, and the basic idea in this example is to have one thread write a result into a promise, and then have multiple threads read that result using a shared future object that they hold. So if we look at the code here, the main function, focusing on this loop here, this loop that's looping 16 times, each time through the loop we're creating a new thread which is going to execute the function consume, which is this function up above here. And this function takes a single parameter f, and the type of this parameter is shared future int. So it's a shared future, and the type of the result that's read out of this future is type int. So when we're looping here, we're going to create a thread that executes the function consume, and we're passing it a shared future as a parameter. Now if we look at the rest of the main function, at the beginning what we do is we create a promise object, p, and it's of type promise int. So the type that of result that we're going to be writing into this promise is of type int. And then what we do on the next line, we take our promise object, we call getFuture for this promise object, which will return the future that's associated with this promise. And then we proceed to call the shareMember function for this future, which takes the future object, converts it to a shared future, and then returns the shared future. So f becomes this shared future that we just obtained that's associated with the promise object p. Then we proceed to create 16 threads in this loop here, each of which is going to execute the code in the function consume, and we're passing in a shared future to each of these threads it's executing. And the shared future will be copied because we're passing by value, and this is not going to move, it's going to copy. So this means that we need to have some kind of object which is copyable, but the shared future objects are copyable, so this doesn't pose any problems. Then the consume function, when these threads start executing, they're executing the function consume, so they're going to call the getMember function for the future f, which will block waiting until the result has been written into the corresponding promise object that's associated with this future f. And when that value eventually becomes available, then the result will be returned by this getMember function, and then it's printed out to standard output. If you go back to the main function, after all these threads have been created in this loop here, we then proceed to write a result into the promise p using the setValueMember function. And in particular, we're writing the value 42, this integer value 42, into p. And as soon as this is done, then all of the threads that are blocked waiting on the futures that correspond to this object P will become unblocked, and then the result can be returned that's been written into the promise. So then basically each thread that's waiting on this get member function here, blocked inside the get member function, it will unblock, return the result that was written into the promise, and it will be printed out. And then of course the main line, or the main function, finishes off by joining with each of the threads that was created. So we've talked about promises and futures and various classes in the standard library that relate to promises and futures. What I want to talk about next is a function in the standard library that's useful in conjunction with futures. And this particular function is called async. It's a template function, and what it allows you to do essentially is to invoke some callable entity, in other words a function or functor, and then grab the return value or any exception that is generated by this function and make it available via a future object. So the function's overloaded, and there's that's why there's two declarations on this slide for the async function. They're a little bit messy because they involve things like this decay. Well, I don't really want to talk about decay in any detail. Just ignore some of these ugly details like decay, and just focus on some of the more basic stuff that's indicated in the declaration. So the async function, the first version of it, it takes a function f, and then whatever parameters are required by this function. If no parameters are required, then basically there's only one parameter, which is just f. In other words, these arguments aren't here if the function doesn't take any arguments. And then we have a second overloaded version of async. The only difference, it has an additional parameter, which is called a launch policy, this particular parameter called policy here. And I'll come back to launch policy in a moment. So again, what the async function allows you to do is invoke the function f with whatever parameters that you want to specify for this function. And when it invokes the function, it will capture any return value from that function or exception if the function throws an exception, and then make those results available via a future object. You'll notice that the return type of async is a future in both of these cases. So what it's returning is a future that allows you to access the value that's returned by the function f, the function that you're actually invoking with async. Now coming back to the launch policy, what the launch policy allows you to control is when you invoke the function f, do you invoke the function f in the same thread that's calling the async function, or do you invoke the function f in a new thread? In other words, do you run the function f asynchronously in a new thread? And this is controlled by the launch policy. The launch policy is essentially a bit mask, and there's two bits that can be set. There's a bit async and a bit deferred. If the async bit is set, what this does is it says that the thread can be run, or the function f can be invoked in a new thread. If the deferred bit is set, then this says that the function f can be invoked in the same thread as the thread that's calling the async function. And because this is a bit mask, it's valid as well to specify both bits. You can set the async bit and the deferred bit. If you set both of them, then what this does is it gives the standard library the choice that it can either run the function f in the same thread as what's the one that's calling the async function, or in a new thread. So either it can run it asynchronously or synchronously in the same thread. And again, when the function f is invoked, if any exception is thrown, the exception will be caught and then stored into the future, so that when another thread reads the result out of the future, then the exception will be rethrown and propagated to the thread that's actually reading the result out of the future. I have one additional comment to make about the async template function, and in particular the comment relates to the future objects that are created by the async function. And in particular, the future objects that are created by the async function behave in a slightly different manner from future objects that are created by other means. And what's different is that when a future object is destroyed, in the case that the future object was created by the async function, when the destructor is called for the future object, if that future object is the last future object that's referencing its underlying shared state, then the destructor for that future object will block until the result associated with the future object becomes ready. This is not the case with future objects that are created by other means other than the async function, though. So this is a peculiarity of future objects that are created by the async function. So this is just something to be aware of. There's sort of a inconsistent behavior in how future objects behave depending on whether they were created by the async function or created by some other means. On this slide we have another example of using promises and futures, and this example is based on an example that appeared a few slides earlier. It's functionally exactly equivalent to the earlier example. The only difference is that the implementation, how it actually achieves the functionality, is different. In this particular example on the slide we're looking at now, we're using the async function, whereas in the previous example we didn't use the async function. And one of the main things to get out of this example is by using the async function we can greatly simplify the code, because essentially the async function can take care of the creation of threads for us. It takes care of the creation of a promise object for us. Therefore we don't need to do this explicitly in our own code. So let's actually look at the example in more detail. So we have this compute value function, which is the same compute value function that appeared in the earlier example that this example is based on. And this function returns a double, which is basically the result of some computation. We're computing the value 42, which is returned by this function compute value. And the idea in this example is we want to execute the compute value function in a new thread, and then have that thread write the result into a promise, and then another thread can read the result out of the corresponding future object that goes with that promise. So if we look at the main function, what we're doing here is we're calling the async function, and we're using async to invoke the compute value function. And we're specifying as the first parameter to the async function the value async, which means run the function asynchronously. So we're going to run the compute value function asynchronously, which implies that internally the async function has to create a new thread and then has to ensure that that new thread invokes the compute value function. And then that new thread, when the compute value function returns, any exception that's produced by that function or the return value that's produced by that function will then be written into the promise that was created by async. And the future object that's associated with that promise is what's actually returned by async. So basically what's happening here, kind of to run through this again, is when we invoke async, because we specify the launch policy async, which means an asynchronous launch policy, what's going to happen inside the async function, it's going to create a promise and then return the future that goes with that promise. So that's the return value that we get back. In addition, it's also going to start up a new thread and make sure that that new thread invokes the function compute value. And then when compute value returns inside this new thread, the new thread is also going to write that return value into the promise object so that it can then be read out of the future object that's returned by this async function. So when the async function returns, we have a future that we can use to access the return value that is being generated by the compute value function. And then on the next line here, we just call the getMember function for this future object, f, to read out the result that was generated. And if we reach the line of code that's calling the get, if we reach the call to get before compute value is actually finished and the result has been written into the corresponding promise, then this will just block waiting until the result becomes available. And then when it finally does become available, because the corresponding promise has been written into, then this will return and give us the value that was written into that promise. But the main thing to notice here, compared to the earlier example, is by using the async function, we no longer need to worry about, in our own code, have to worry about explicitly creating a new thread to run the compute value function in. Also, we don't have to explicitly create a promise object, because all of this is done inside the async function for us. So it greatly simplifies the code compared to the earlier example that we had, where we had to explicitly create our own thread and also explicitly create our own promise object and then get a future that goes along with that promise object. On this slide we have an example of using futures in conjunction with exceptions. So let's look at the code in more detail. We have a function called square root that takes a single double parameter x and it returns a double, which is the square root of x. If we look at the code for the function, we first check to see if x is negative, because if x is negative then it doesn't make sense to take the square root of x. So in this case we throw an exception indicating that we're trying to take the square root of a negative number. Otherwise we return the square root of x. If you look at the function main, we have a vector of doubles called values, which stores values that we want to compute the square root of. So 1.0, 2.0, and minus 1.0, we're going to later compute the square roots of these values. Then we create a vector of futures called results, which is going to store futures that we'll use to access the square root values that we've computed. And then we go into a loop here, looping for each of the values in our vector called values, 1.0, 2.0, minus 1.0. We're going to loop over each of the elements in the vector. So x corresponds to one of the elements in our vector. And we're going to invoke the square root function for each of these elements x using the async function. So when we call async, what this is going to do, it's going to cause square root to be invoked with this parameter x, and the return value, or the value that's produced by this square root function that's invoked, will be accessible via a future that's returned by the async function. So async returns a future, we store this future with pushback into the vector results, and then later on we'll look at the future values that are stored into this vector in order to access the square root values that were computed. So this is what we do next. We loop over each of the elements in our vector of futures, which is called results. So x here corresponds to a future. And then what we're going to do is we're going to call the getMember function of x to get the square root value that was computed and then print it out to standard output. But because the function that we were invoking with async can throw an exception, because we're invoking the square root function, but square root can sometimes throw an exception here, it's possible that when we call the getMember function, this may throw an exception, because if the result that was written into the promise that corresponds to this future was an exception, then when we call get, it's going to rethrow that exception. So because an exception can be thrown, in particular a domain error exception may be thrown, this is why we're using a try-catch block here. So we call get, hoping that everything went okay, and there wasn't an exception that was produced as a result of calling the square root function, and we can actually read out the square root that was computed. And if that's the case, then everything works fine. We get the value, and then we print it out, and everything is okay. But in the case that an exception was generated in the square root function, then that exception will be rethrown here. And it would have been a domain error, because the only type of exception that's thrown by the square root code up above here is a domain error. So if an exception was thrown, we'll go into the catch block, and we'll just print out a message saying that an error had occurred, basically during that square root computation. So this is just an example of showing how futures can be used in conjunction with exceptions. Remember that futures can hold not just like a value for their result, but they can also hold an exception for the result, in which case when the getMember function is called for that future, this will result in the exception being rethrown. In the standard library, another class that's quite useful in conjunction with futures is the so-called package task template class. And this particular class provides a wrapper for a callable entity such as a function or functor that makes the return value from that callable entity available via a future object. So the declaration of the package task template class is as shown here. It's templated on the return type of the callable entity, in other words, the return value of whatever function or functor is associated with the class, as well as the arguments of that function or functor. For those of you who are familiar with the function template class in the standard library, the idea behind the package class template class is very similar. The main difference being that in the case of the package task template class, the result that's produced by the callable entity, the function or functor, is made available via a future object, whereas this is not the case in the case of the function template class in the standard library. The package task is often used as a thread function, in other words, for the function to be executed by a thread or functor to be executed by a thread. The package task template class, the objects of this class are movable but not copyable. And there's a member function called getFuture, which is provided by the package task template class. And this provides access to or allows you to retrieve the future that's associated with the package task. Because when the package task invokes whatever functions associated with it, it makes the result available via a future. There has to be a way to get access to that future object so that the result that was produced by the function invoked by the package task can be accessed. And the getFuture member function can only be called once. It can't be called multiple times. On this slide we have a summary of the members for the package task class. With respect to construction, destruction, and assignment, really the only comment to be made here is just a reminder that objects of type package task are movable but not copyable. The more interesting functions are the ones listed on the bottom part of the slide. So we have a member function called valid that checks to see if the package task object is currently associated with any shared state. The swap function, which swaps the contents of two package task objects. The getFutureMember function allows the future object that's associated with the package task to be retrieved. Then the function call operator allows the function that's associated with the package task to be invoked. Or maybe more generally, I should say callable entity. It could be a function or it could be a functor, for example. Make ready at thread exit is similar to the function call operator, except that the result that's produced by the function that becomes made available via a future object, it only becomes available via the future object once the current thread exits. So it potentially delays a little bit the time before the result becomes available. And finally, we have the reset member function, which resets the shared state associated with the package task. On this slide, we have an example of using the package task class. So let's look at the code in more detail. In the main function, we create a package task object called PT, and the package task template class is instantiated with the type int bracket bracket, which means that the callable entity that's associated with this package task, it returns an int and it takes no parameters at all. So when we pass a callable entity to the constructor of the package task, in this case the callable entity specifically is a function called getMeaningOfLife. And if we look at the code for getMeaningOfLife, it's a function that takes no parameters and it returns an int. So it matches the type here because the function should take no parameters and return an int. So this is going to create a package task that's associated with the code in the function getMeaningOfLife. Then on the next line here, for our package task object, we call getFuture, which gets the future or retrieves the future object that's associated with this package task, and then we save this in F. Then we proceed to create a new thread, which is associated with the thread object T, and the code that's going to be executed by this new thread is the code that's associated with our package task. We have to use the move function here because package tasks, remember, package task objects are not copyable, they're only movable. If we left out this move here, then we would attempt to copy the package task and this would generate a compile error. So we need to move it, so we use this move function here to cast the type of PT into something that's amenable to a move operation. And then on the next line, we detach our thread, T, so that it can run independently. And then the next line, we call the getMember function for our future F. So this will block until the result is available that's associated with the future. And if we look at the code that's going to be executed, that's actually going to produce the result that we read out of the future here, it's going to be the thread that's associated with this package task. So this package task is going to invoke getMeaningOfLife, which sleeps for 1 second and then returns the value 42. So in this other thread, we're going to invoke getMeaningOfLife. It's going to sleep for 1 second, then will return the value 42, and then this value 42 will then be written into the promise that's associated with the future that we're waiting on here, and then that value will become then the thread here can read the value out of the future that was written into the corresponding promise and print the result here. On this slide, we have another example of using the package task class, and in this particular example, the underlying callable entity or function in this case that's associated with the package task is going to be one that takes some parameters or arguments. So if we look at this code in more detail, we have a function called power, which just computes an exponential. We have two double parameters, x and y, and this just computes the power x raised to the power y, essentially, and returns that as a double. And what we want to do in this example, we want to use package task to invoke this function power in the same thread as the caller and then in a different thread from the caller. So if we look at the main function, First, we're going to invoke the function associated with the package task, which in this case is going to be the function power, in the main thread. In other words, the thread that's executing the main function. So we create a package task called task, and we specify for the callable entity associated with this package task, which in this case is a function, we specify power, which is this function up here. So when this package task is actually invoked, it's going to invoke this function power. And the type that we're plugging into the package task, because package task is a template class, so the type that we're plugging in for this template parameter is a function that returns a double and takes 2 double parameters. So this matches the type of this power function, which if you look above here, it's a function that takes 2 double parameters and returns a double. So this the signature of this function matches the type here. Then we proceed to call or invoke the package task, which is going to indirectly cause the function power to be invoked with the arguments 0.5 and 2.0. And then when the function power returns, the value that's returned by this function will be captured and made available via a future. So in order to gain access to the value that was produced by invoking the function power through this package task, we then need to take the package task and get the future that's associated with it so that we can obtain the value that was returned by the underlying function power. And then we get the data or result that's associated with that future. So this will print the result that was returned by the power function. Then we reset the package task because we're going to use it again. And in this case, we again get the future that's associated with this package task after it's been reset. And now we're going to create a new thread. And the new thread is going to execute the code that's associated with this package task. We're providing the parameters 2.0 and 0.5 to be passed to the underlying function associated with this package task. In other words, when the package task invokes the function power, it's going to pass 2.0 and 0.5 to the function power. Then we detach the thread by calling detach on the thread object, T, which will cause the thread to execute independently from the main thread. And then we call the getMember function on the future f, which we saved up above. F was the future that's associated with our package task. So this is going to get the result that was produced by invoking the power function in this new thread that we've created on this line here that's associated with the thread T, the thread object T. So this, of course, will the getMember function will block until the result is ready and then return the result that was written into the future.